performance. Our learning goals and objectives are 1, to know how to add impedances in series and in parallel, and to 2, know why impedance is a complex quantity. So, in general, the reason why we talk about impedance for alternating current is because it makes life simpler. So, previously in DC circuits, we talked about how you add things when they're resistances, how you add things when they're inductors, how you add things when they're capacitors. But in the world of impedance, you treat everything as the same. So you write it as, the impedance is usually written as Z, and it has a resistive part, R, plus I, which is the imaginary number, times reactive part. So this, so this part is so the resistive part dissipates energy, and the reactive part stores energy. So, more or less everything we learned in DC circuits can apply. So, for instance, what you do is for two impedances Z1, Z2 that have the same current, you can simplify them by saying Z total equals Z1 plus Z2. And it doesn't matter if it's a resistor, an inductor, or capacitor, you just add their impedances. And if they're in parallel, Z1, Z2, so they have the same voltage across them. The Z total will be equal to 1 over Z1 plus 1 over Z2. And this doesn't matter if they're resistors, inductors, or capacitors. All you need to do is remember the what the impedance is for that given circuit element. So hopefully now you have an idea of the impedance is a complex quantity. So there's a real part which loses energy and an imaginary part which stores energy. The reason why we go into complex quantities is because it makes math and analysis in the AC circuits much easier if you use complex quantities. So now what we can do is we can write down a resistor, and then we'll say what the impedance is for each one of these. We'll make a little table. So inductor, and then capacitor. So resistor is just going to have an impedance R. It's just going to be entirely real. So as you know from DC circuits, a resistor just dissipates energy. It doesn't store any energy. An inductor is going to have an impedance that's just minus I omega L. So it only has a reactive part of its impedance, so all an inductor does is just store energy. And a capacitor is going to have an impedance that's equal to I over omega C. And once again, its impedance, all it does is it stores energy. So resistor only has a real part, an inductor, so if you end up with something that has a negative, an imaginary part, so say you have an impedance that's only imaginary and it's only negative, then it behaves like an inductor. Say you have an impedance that is only imaginary and only positive, and it behaves like a capacitor. So let's take an example. If we have a resistor, ZR, an inductor, ZL, a capacitor, ZC, all in series, then to find the total resistance, we just add them all up. It's the resistance plus the inductance impedance plus the capacitive impedance. That's pretty much it. So the only other thing that I would be remiss not to say is that I squared is equal to -1. So in this case, I is equal to the square root of -1. And if you rewrite this as I times I equal to -1, then I equals -1 over I. So if you wanted to rewrite this capacitor, you could also rewrite this as -1 over I omega C. But I was just trying to be consistent that having an I times some reactance and an I times some reactance. Alright, thank you very much.